Hey everyone, and welcome. Today, we're going to break down two ideas that are absolutely central to thermodynamics, enthalpy and internal energy. Now, they both measure energy, but, and this is the important part, they do it in really different ways. So, let's get right into it.
Okay, so picture a chemical reaction bubbling away in a beaker. You can feel the heat coming off it, you can see things happening, there's obviously energy being released. But how do we actually measure all of it? I mean, not just the heat, but the whole shebang. That's the big question, right?
Well, to answer that, we need two different tools. First, you've got internal energy, which we call U. Think of this as the system's private stash of energy, everything that's happening strictly inside its own little world. But then you have enthalpy, or H, which is more of a total, public accounting. It includes that internal energy, plus any energy the system spends doing work on its surroundings.
All right, let's put some real definitions to these names. Once you get these down, you'll see exactly how and why they're different.
So first up, internal energy, U. This is literally the sum of every bit of energy inside the system's boundaries. You know, all the molecules vibrating, spinning around, bumping into each other, plus all the energy that's locked up inside their chemical bonds. It's all that internal chaos, totally self-contained.
Now, enthalpy, H, takes all of that internal energy and it adds one more crucial thing to the pile. It also accounts for the energy the system needs to just, well, to make space for itself, to push back against the pressure of the outside world. That's why the formula is H equals U plus this PV term.
So, you're probably wondering, how are these two actually connected? It really all comes down to one single elegant equation.
At its heart, the difference really just boils down to a simple idea: work. Specifically, the work a system has to do when it expands. I mean, think about it. If it gets bigger, it has to push the rest of the universe out of the way, and that takes energy.
And here it is. This is the equation that ties it all together. It says the change in enthalpy is equal to the change in internal energy, plus this little term on the end, P delta V. And that term, that's the energy cost of doing that pushing, of changing its volume.
Okay, but what does that P delta V thing really look like in the real world? Imagine a reaction happening in a cylinder with a movable piston. The reaction happens, and it produces a bunch of gas. Now, that gas doesn't just appear. It has to physically push that piston upwards against the pressure of the atmosphere. That pushing, that is work. And the energy it costs to do it is exactly P times delta V.
Okay, now that we have our master equation, let's see what happens when we apply it to a really common situation: reactions that only involve solids and liquids.
I mean, just think about it. If you mix two liquids together, does the total volume really change all that much? Nah, not really. Solids and liquids are already packed in pretty tight. They don't expand or shrink in any meaningful way. So their change in volume, their delta V, is just incredibly tiny.
So if that delta V is basically zero, what happens to our P delta V term? Well, it pretty much vanishes. It becomes so small we can just ignore it. And that means for reactions with just solids and liquids, the enthalpy and the internal energy are practically the same number.
But, and this is a big but, everything changes when you let gases into the mix. This is where the difference between these two types of energy becomes a really big deal.
See, unlike solids or liquids, gases are all about volume. A tiny pinch of a solid can explode into a massive cloud of gas. That means for any reaction that makes or uses up gas, the change in volume, delta V, can be absolutely huge. You just can't ignore it. The system is doing a lot of work on its surroundings.
And so, when gases are in play, we have to bring back the full equation. That P delta V term isn't tiny anymore. It's a significant chunk of the energy, and it makes enthalpy and internal energy two very distinct values.
Now, you might be thinking, actually measuring the change in volume of a gas sounds like a real pain. And you know what? You'd be right. But luckily, scientists have figured out a really clever shortcut to get around it.
So how does it work? Well, instead of trying to measure that messy change in volume, we can use a trusty old friend, the ideal gas law. This law lets us connect volume directly to something that's way easier to track, the number of moles of gas. So we can just swap out that tricky P delta V term for something much more user-friendly.
And voila! This is what you get. A super powerful and, more importantly, practical equation for any reaction with gases. The change in enthalpy is just the change in internal energy plus the change in the moles of gas times a couple of constants. No more messy volume measurements.
Now, the most important piece of this new puzzle is that delta N sub G, and I gotta stress this, it only counts the gases. You completely ignore any solids or liquids in the reaction. You just take the number of moles of gas you end up with and subtract the moles of gas you started with. That's it.
All right, we've covered a lot of ground. So let's boil it all down to the bottom line and answer that first big question. When are enthalpy and internal energy pretty much the same thing?
So, here it is. They're effectively equal under two main conditions. First, if your reaction only has solids and liquids, no real volume change means no work is done. Simple. And second, even if there are gases, if the number of gas molecules at the end is the same as the number you started with. If delta N is 0, that whole work term just disappears, and once again, the two values are the same.
And that leaves us with a pretty cool idea to chew on. We've just seen that even a tiny chemical reaction has to spend energy just to push back against the universe around it. It kind of makes you wonder, if every little energy exchange everywhere has to account for this kind of work, what does that imply for the total energy budget of the entire cosmos? Something to think about. Thanks so much for watching.